You've just invested heavily in high-density AI and GPU servers. These are the Ferraris of compute. But underneath that hardware, you're running them on the electrical equivalent of bald tires. When legacy power fails, the whole rack goes dark. Most physical infrastructure vulnerabilities remain hidden during normal operations. Because power systems don't throw software errors as they age, IT teams often don't realize their hardware is degrading until a critical failure occurs. This creates what we call a liability tail. It is the accumulation of technical and financial debt that grows every day an aging power system stays in production. Your infrastructure can pass a basic daily diagnostic and still be one unexpected power event away from a total system crash. Underneath the chassis of almost every standard UPS is a sealed lead-acid battery. These batteries possess a predictable chemical lifespan of 3 to 5 years, and they degrade regardless of how often they are used. This leads to the green light illusion. A UPS can pass a self-test while idle because the internal resistance hasn't been challenged by a real-world load. This chart tracks battery failure risk. For 4 years, risk stays low, keeping you in the green zone. At year 5, the line spikes. This is the chemistry cliff. By year 7, aging electronics make the unit a primary failure liability. Ignoring the chronological age of these chemical components transforms your safety net into the exact mechanism that will trigger your next outage. Modern facilities are moving away from lead acid in favor of lithium iron phosphate, or LFP. Transitioning to LFP technology extends the safe operational lifecycle to a full 10 years. This aligns your power infrastructure with the lifecycle of the servers themselves, reducing maintenance touches by 60%. This technology is increasingly necessary because of how modern servers consume energy. When a cluster of GPU or AI servers boots up, they pull violent power spikes known as inrush current. Older UPS inverter boards cannot react fast enough to these step-load demands. They often interpret a rapid GPU spike as a short circuit, causing the UPS to cut power to protect its own internal components. Lithium iron phosphate handles deeper discharges and rapid cycling without the chemical lag seen in lead acid. It provides the superior ride-through needed to sustain power during these high-density demands. Because LFP supports these violent spikes without dropping voltage, it prevents the UPS from tripping its own safety breakers. This shift synchronizes your power delivery with the physics of modern high-performance computing. IT teams frequently create a single point of failure by plugging one power supply into a UPS, the A side, and the second directly into a wall outlet, the B side. This diagram shows the risk. While the A side is protected, the B side is exposed to raw, unconditioned utility power, making it a wide-open door for infrastructure failure. When a backup generator starts, it often creates dirty power as the engine hunts for a steady frequency. You can see the waveform on the B side fluctuate violently during this transition. These frequency shifts cause modern, high-efficiency power supplies to initiate a hard reboot. Even if your A side is stable, the server crashes because the B side path failed. True redundancy requires both power paths to be conditioned. Without a secondary protection source, your B side setup guarantees downtime during power transitions. We also have to consider the efficiency of how power is delivered to the rack. North American server closets have relied on the 110-volt standard for decades. To support larger deployments on these legacy circuits, organizations often bolt step-down transformers onto their UPS systems to accommodate 110-volt cords. These transformers experience core and copper losses, bleeding 3 to 7% of their electrical load as pure waste heat. This creates a double financial penalty. You pay for the wasted electricity, and then you pay for the additional air conditioning required to cool the heat the transformer radiates into the rack. Upgrading wall receptacles to native 208-volt power changes the math. As you can see, the same 30-amp circuit delivers 2.8 kilowatts at 120 volts, but 5.0 kilowatts at 208 volts. Phasing out transformers and switching to 208 volts doubles your usable compute capacity on the same physical copper wiring. This allows you to scale density without expensive electrical panel overhauls. These technical vulnerabilities eventually impact the corporate balance sheet through cyber insurance policies. Cyber insurance providers have become surgical in their post-event audits. They specifically search for neglected physical infrastructure as a reason to deny downtime claims. Auditors look for pre-2021 date codes on UPS units. These codes serve as objective evidence that the infrastructure was neglected, providing carriers with a reason to deny a payout. Surviving these audits requires documented, reasonable care. This means maintaining logs of battery replacements and load testing to prove you protected the data. Documented proof of maintenance serves as a financial safeguard, ensuring the organization can demonstrate compliance during a post-event audit. Addressing the liability tail doesn't require an immediate capital overhaul. It begins with mapping the hidden risks inside your current environment. The Schneider Electric EcoStruxure IT Health Assessment is a diagnostic tool designed to provide this visibility. The assessment generates a report like this one, showing UPS health scores, battery wear metrics, and power usage effectiveness to identify inefficiencies. If you initiate the assessment through the link provided, you will also receive a complimentary copy of the book Hyperpower to help guide your infrastructure strategy. Taking 20 minutes to run this assessment converts your hidden liabilities into a documented baseline, providing the objective data needed to justify modernization to your leadership.